If you are a regular of these natural history talks, it is very likely that you live by or near the North Sea. So it wouldn't be a surprise if you already knew about some of the themes I plan to discuss today. In which case, I hope you will still nonetheless be able to enjoy having these topics rehearsed for you. Knowledge, like good music, is oftentimes best enjoyed when revisited. If, in contrast, this is all news to you, then, well, even better. I hope that you will find the subject of this talk as fascinating as I do. My name is Miguel Morales Maqueda. I am a lecturer in physical oceanography at Newcastle University, and so I am going to tell you about the oceanographic history of the North Sea in the last 20,000 years or so. The North Sea, as we are going to discover, has a most accidented timeline. The image shown on this slide was taken on the 1st of July 2015 by the Moderate Resolution Imaging Spectroradiometer, MODIS for short, on NASA's Terra satellite. MODIS is incidentally producing one of the richest collections and probably the most beautiful of remotely sensed images captured from practically every corner of the planet. This one shows the entire North Sea. Clouds cover parts of the northern and western edges of the North Sea area. And we can also see snow still sitting on the mountains of southern Norway. The water is mostly dark blue, but the milky light patches are likely the result of a bloom of microalgae. These blooms are common in the North Sea in late spring and early summer, when waters are warming and winds cause turbulence in the water. This turbulence brings to the surface the nutrients that microalgae need in combination with sunlight to photosynthesize. These microalgae form part of a vigorous food web that has made of the North Sea one of the richest fishing grounds in Europe for hundreds of years, at least until the early 1980s, when stocks dramatically declined due to overfishing. Fishermen have been fishing in the North Sea for herring, cod, plaice, and many other species since the 9th century and probably earlier. This painting shows a 17th century Dutch fishing boat called a dogger. Now, here it is. Doggers were commonly used in the North Sea for fishing cod, and they gave its name to Dogger Bank in the central North Sea, of which we will have much more to talk about shortly. One reason why the North Sea is so rich in nutrients and so capable of supporting a potentially very abundant life is because it receives the runoff of large northern European rivers. But another equally important reason, if not more important, is that it is a very shallow sea with a mean depth of only about 80 meters. And so the turbulent motions caused by the strong winds and tides that crisscross the North Sea can easily reach the seafloor and bring nutrients all the way up to the surface. Shallow seas, such as the North Sea, are known as shelf seas and are almost invariably coastal waters surrounding land. Cartographers, by convention, mark the limits of shelf seas at the point where the water depth exceeds 200 meters. The chart on this slide shows the global altimetry, that is, the elevation of emerged lands above sea level, and the bathymetry, the depth of the ocean below sea level. The light blue areas around the continents are the shelf seas. Shelf seas amount to only about 7% of the total ocean surface, but vary largely in size. In certain regions, the continental shelf and the shelf sea above are very narrow, such as, for example, around the Iberian Peninsula here. In other areas, in contrast, shelf seas can extend for hundreds and thousands of kilometers. The North Sea, for example, just farther north, is quite wide, spanning around 1,000 kilometers from south to north and 600 kilometers from east to west. And the Arctic shelf seas are at some points over 1,500 kilometers wide. Probably obvious, but nevertheless intriguing aspect of shelf seas is that they are very sensitive to changes in sea level, to the point that many shelf seas have oscillated in and out of existence during the last 1 million years because of periodic glaciations during which large volumes of seawater were removed from the ocean and accumulated on land in the form of snow and ice. This transfer of water from ocean to land caused dramatic drops in sea level and the partial or total drying of many shelf seas. In return, during deglaciation periods, coastal areas that had been previously drained became flooded, and shelf seas were born or reborn in many cases. Large pulsations of sea level are key drivers of the natural history of shelf seas. And it is these pulsations in sea level that we are going to discuss in the following slides, progressing backwards in time from the modern era to the last glacial maximum. So let us start by looking at sea level changes at present. Sea level rise figures very prominently amongst the impacts of global warming and the attending climatic change. Estimates of how much sea levels are going to increase globally are rather uncertain, and this uncertainty results not only from our incomplete understanding of the climate system, but also, and perhaps more importantly, from the fact that future warming rates will depend strongly, as they have in the past, on complex economic, political, and technological choices made by over 7 billion humans with greatly diverse cultures, values, lifestyles, and aspirations. The one thing that is certain is that climatic changes are very much happening now, and so is sea level rise. This figure shows the estimated global average of sea level rise since 1880. The jagged, thin blue curve is a composite of data obtained from tide gauges. The thick blue line is a smoothed version of the same data, this one. And the red curve has been created using satellite data. It's just the curve towards the end of the time series. Satellite data have been available since the 1990s or so. The gray shading represents data uncertainty, which decreases as the quantity and quality of data have increased. Global sea level has risen by about 20 centimeters since the late 19th century. And it is obvious that the curve does not hint at a decline in the rate of increase in the near future. If anything, the growth has been fairly steady over the last 100 years or so. And in fact, predictions for the next 100 years oscillate between an additional 20 centimeters of sea level increase and a rather more alarming rise of over 1 meter. There are two main mechanisms that cause sea level to change at a global scale. The first mechanism is thermal expansion. Like any other substance, seawater responds to a rise in temperature by expanding, and this expansion translates into a sea level rise. The second mechanism is the input of extra water into the ocean as a result of the melting of tropical, temperate, and polar glaciers, as well as ice caps and ice sheets. In the last decade or so, melting has contributed about 60% of the total sea level rise, while thermal expansion accounts for the remaining 40%. But the contribution from thermal expansion was probably much higher in the last century before the thawing of polar ice started to accelerate. In the 8 years between 2002 and 2014, shown in the graphic, thermal expansion and melt contributed in about equal proportions to sea level rise. Forecasts of sea level rise by more than 1 meter by 2100 reflect the expected increasing weight of the mass input contribution to sea level rise in the coming years. The amount of water currently stored in ice sheets is quite considerable. In 2013, National Geographic magazine published a fascinating article showing maps of how the emerged land masses would look like if all the ice on Earth had melted into the sea. Global sea levels would rise by a staggering 66 meters. The coast of Europe would change dramatically in this scenario, and this is shown in this figure. Large areas of Northern Europe, half of Belgium, most of the Netherlands, large portions of the German coast, practically all of Denmark, and large parts of Finnish and Russian Karelia would be taken by the sea. In eastern England, Lincoln, Norfolk, Suffolk would largely go, as well as Greater London. And further south, the map reveals that the Black Sea would join up with the Caspian Sea. This catastrophic and most unlikely scenario highlights the point that many areas of Northern Europe, including southeastern Great Britain, are low-lying lands exposed to the sea and easily threatened by rising sea levels. It has been so for a very, very long time. We have just seen that the North Sea coast of England is vulnerable to sea level rise in the future. Well, it has also been so, and very much so, in the past. This map shows the kingdoms into which what is now England was divided in the 6th century. What interests us in this map, though, is not the history of Dark Ages Great Britain, but the fact that large areas of the eastern coast of the island, which are now dry land, were at the time swamps and marshes. Notably the fens and the Humber estuary. These areas were tidal mudflats and salt marshes affected by the twice daily flood and ebb of the tide and exposed to storms and storm surges. all along the coasts of the southern North Sea, a way of protecting coastal inhabited areas against the advance of the sea has been historically the construction of tall mounds up to 15 meters high, out of reach of even the highest tidal high waters in the North Sea. In Frisia, these artificial dwelling mounds are called Terp. The photograph here shows a Terp on Hallig Hooge in the North Frisian Islands. Yes, in this area. Terpen were built along the Wadden Sea coast since 500 BC, and it was only in the 12th and 13th centuries, when dikes started to be widely used, that the construction of terpen stopped. And this brings us back to England in the 6th century. The Middle English word thorp, which denotes a hamlet or small settlement, has the same root as terp. And it is tempting to speculate that some of the place names with the suffix thorp or thorpy along the English coast of the North Sea could refer to sea-protected terpen. For example, could Scunthorpe, which appears in the Domesday Book of 1086 as Scumasthorpe or Scumas homestead, have originally been a terp in the Humber estuary? Why have terpen or thorps been so widespread in the North Sea for so long? Remember that we have just said these structures date back to at least 500 BC. To understand this, we need to look at past changes in North sea level. This curve shows estimates of sea level in the southern North Sea since 2500 BC. Values are in meters, but the actual numbers on the graphic, which are given relative to what is called the German normal null, are less important to us than the relative change. We see that the net sea level increase over the last 4,500 years or so amounts to about 4 meters. This sea level rise, however, has not been steady. We can see that there are repeated episodes of sea level advance and retreat, what geologists call transgressions and regressions. Sea level can rise or fall by several meters on time scales of a few hundred years. For example, between 1000 and 500 BC, in the pre-Roman Iron Age, there is a period of relatively low sea level that was terminated by a rather rapid rise of well over 2 meters in the following 300 years. That is a sea level rise rate of over 8 millimeters per year, 3 times larger than the rise rate we are currently experiencing globally. At the time, sea levels would have risen by almost 1 meter over a period of just 3 generations. Maybe this goes some way towards explaining why terpen started to be built around 500 BC along the Frisian coast. And we can only imagine the stories that elders living in Frisian coastal dwellings in that period could have told their grandchildren about how much farther north the sea was when they were young. The detailed causes of these oscillations in sea level are not well understood, among other things because the techniques used to infer past sea levels carry significant uncertainties. The ones used to create the figure shown here involve locating, dating, and investigating the composition of peatlands in coastal areas. Peats are proxies for sea level changes because the presence of peats requires a change to freshwater conditions and therefore a retreat of sea level. Methods used in other sea level studies identify, count, and date marine or seawater tolerant microalgae present in salt marshes soil, and use the presence and abundance of these algae as proxies for past sea level changes. Despite its inherent uncertainty, especially the farther back in time estimations go, these techniques reveal a consistent, if not fully understood, dynamics. But this is only the tip of the iceberg. sea level reconstructions go well beyond, back beyond 2500 BC. This graphic, of which the previous is only a section, shows the entire sea level history of the southern North Sea going back to around 8000 BC, when sea levels in the North Sea were over 50 meters lower than at present. Now, if we look at a chart of the North Sea's seafloor relief, what oceanographers call the bathymetry, we realize that if sea levels drop by 50 meters, the area of emerged dry land would extend inward into the North Sea by hundreds of kilometers relative to the present coastlines. In the southern part of the North Sea, only a few narrow depressions would remain permanently connected to the open sea. Doggerland, a large and shallow bank of sand about 100 kilometers east of Great Britain, would become an island, the shallowest point of Doggerbank being on only 15 meters of depth. According to the curve shown in the previous slide, this point would have become fully submerged after 6000 BC. This second chart indicates the location of a vanishing Dogger Island. There is a speculation that a tsunami with waves of probably over 20 meters that occurred at about the same time caused the final disappearance of an already vanishing Dogger Island. This mega tsunami was triggered by a submarine landslide off the coast of Norway, the Storega landslide, which has been extensively documented in many areas of the North Sea. It is also obvious from the chart on the right that the Strait of Dover did not exist 9,000 years ago, as the area east of what is now the Strait of Dover must have been all land at the time. The connection between what is now the English Channel and the North Sea southern bights occurred only as recently as 7000 BC or so. It was a very different, indeed, world then. A world shaped by the glaciation, the melting and collapse of the enormous ice sheets that had covered North America and Northern Europe at the time of the Last Glacial Maximum 20,000 years ago. The glaciation caused the global sea levels to go up by about 135 meters in just 15,000 years. That is a rate of almost 10 millimeters of sea level rise per year. The geological origin of Doggerbank gives testament to the existence of a large ice sheet at the time of maximum glaciation in Northern Europe, with the bank being no other thing than a huge moraine or accumulation of debris and rocks that was deposited at the southern limit of the ice sheet in this area. We shall discuss shortly how the North Sea looked like in the coldest period of the glaciation, but let us first return to the North Sea of between 7,000 and 11,000 years ago, a period which is called the early Holocene. This map is a beautiful reconstruction of continental Europe above sea level 7,000, 8,000 and 16,000 years before present. Many features shown in the map are necessarily speculative, since we do not know enough about the geography of the area at the time to chart it in detail. In this idealized picture, what is now Doggerbank was in 7000 BC a rather large island separated from the mainland to the south by a narrow and shallow channel called Outer Silver Pit. Other reconstructions suggest that the Strait of Dover was already open at the time, and that the relatively deep southern bights of the North Sea was already connected to the wider Atlantic by the English Channel, but this is not shown in this map. As we continue to go back in time, we see that 1,000 years earlier, the entire southern part of the North Sea was dry land. This area was named Doggerland in the 1990s and it has been the object of considerable and fascinating research by British and European teams who have mapped parts of the region using seismic reflection data generated by the oil and gas industry, and have also sought to reconstruct the natural and human environments of the region during the Mesolithic era, so the period spanning between 13,000 and 3000 BC, from the last glacial maximum to the Neolithic revolution. There is indeed evidence recovered from the seafloor of remains of plants, of animals, and of human habitation, for example, tools, bones, and built structures. This evidence allows experts to reconstruct, to some extent, the environment of this now submerged land. It is likely that this area was populated in the Mesolithic period, as far back as 13,000 BC, by hunter-gatherers, possibly living on prey such as reindeer, mammoth, horse, elk, and aurochs. Coming back to the map, we can see that around 16,000 BC, so only 2,000 years after the last glacial maximum, Northern Europe was a much larger place than it is today. It extended well west of modern Ireland and up to the Shetlands in the north. The English Channel was then a deep river valley collecting the waters of ancient versions of the Thames, the Scheldt, the Meuse, and the Rhine into a vast channel river discharging west of modern Brittany. We also see in the map what was left at the time of the Celtic Fennoscandian ice sheets that had covered a much larger part of the continent just a couple of thousand years earlier. This is how Europe might have looked at the time of the last glacial maximum. 3 ice sheets covered most of northern Europe: the Celtic ice sheet, the Fennoscandian ice sheet, and the Barents ice sheet. This last one was located northeast of the Fennoscandian ice sheet and is not shown in the map. These 3 ice sheets contained a volume of water almost 3 times larger than the present-day Greenland ice sheet. Particularly interesting for our subject is the fact that an ice bridge joining the Celtic and Fennoscandian ice sheets covered the northern North Sea, this region. South of the bridge and south of what is now Doggerbank, there was a proglacial lake, that is a lake that is formed through damming by a moraine or a glacier. This lake was approximately 750 square kilometers in extent. For comparison, this is larger than the total area of standing inland water in present-day England, which is about 675 square kilometers. But the Eurasian ice sheet was in fact the smallest of the 2 massive ice sheets that formed in the northern hemisphere during the last glaciation. The Laurentide ice sheet that covered all of modern Canada and large parts of what is now northeastern United States was approximately 4 kilometers thick and contained over 30% more ice than Antarctica holds today. The water necessary to form all of these ice during the last glaciation came from the ocean. Where is it from? Best estimates of the equivalent sea level change caused by the accumulation of frozen water on land indicates that at the last glacial maximum, about 18,000 BC, global sea levels were between 130 and 140 meters lower than today. This is about the height of St. Peter's Basilica in the Vatican. The chart in the slide allows us to visualize the implications of this dramatic fall in sea level for the distribution of emerged lands across the Earth. At first sight, nothing much seems to have changed compared to the modern outline of the continents. All continents and islands are very much recognizable. But if we look in more detail, remarkable differences become apparent. We already talked about the westwards and northwards expansion of continental Europe as a result of the drying and glaciation of the Barents, Baltic, North, Irish, and Celtic seas. But many other new lands had emerged across the world during the glaciation. For example, the region of Beringia is at present divided by the Bering Strait into two parts, one in Siberia, stretching westwards to the Lena River, and one in modern Alaska and Canada, bounded on the east by the Mackenzie River. But at the time of the last glacial maximum, Beringia was a much larger continuous mass of land joining the Eurasian and North American continents. The dark green color on the map delineates the expanded boundary of Beringia then. It is believed that shortly after the end of the last glacial maximum, humans moved from Siberian Beringia into North America to populate eventually the whole continent. Another example, Australia and New Guinea were then joined across what is today Torres Strait, and the Gulf of Carpentaria was a large inland lake. This enlarged austral continent has been called Sahul. At the same time, the Malay Peninsula and the islands of Sumatra, Java, and Borneo were part of a larger landmass, Sundaland. It is likely that the original colonizers of Sahul migrated from Sundaland at some point between 45,000 and 70,000 years ago, well before the last glacial maximum, but well within the last glacial period, which started over 100,000 years ago. A final example, amongst many others, the Argentine continental shelf, which extends out all the way to the Falkland Islands, expanded by as much as 500 kilometers eastwards during the last glacial maximum. The total area of emerged lands at the last glacial maximum was over 20 million square kilometers larger than it is today. This is more than twice the area of continental Europe, from the Urals to Finisterre. A good fraction of this land was, however, covered by ice. It gives pause for thought the fact that such major changes in the distribution of lands and oceans and the implications of these changes for life on Earth and for human evolution and migration are caused by a process apparently as simple as the transfer of water between ocean and land and the attending changes in sea level. But the actual process is, in fact, rather complex. The diagram shown on this slide depicts the three stages involved in a glaciation-deglaciation cycle. For the sake of a clear visualization, the geometry, both horizontally and vertically, has been exaggerated. The top panel shows a cartoon of land and ocean in some unglaciated region of the world. Prior to glaciation, the Earth's crust, or lithosphere, is shown lying on top of the mantle, which is rocky but denser than the lithosphere and in constant slow motion in response to geothermal forces within the Earth's interior. As glaciation proceeds, as shown in panel B, seawater evaporates and falls over land in the form of snow that accumulates and ultimately transforms into ice. An ice sheet forms then. And this ice sheet, by virtue of its weight, depresses the crust and mantle below. Mantle layers underneath the crust are deflected sideways under this load, and this causes the formation of what are called peripheral bulges along the edges of the ice sheet here and here. The bedrock moves upwards rather than downwards where a peripheral bulge occurs. Along the coast, sea level decreases not only because water is being transferred from the ocean to land, but also because as the peripheral bulges develop, the elevation of the coast increases relative to that of the water. There is an effect that partly compensates for the drop in sea level, and this relates to the gravitational attraction exerted by the ice sheet on the nearby coastal water, but we will not consider this effect here. During the glaciation, as shown in panel C, the opposite processes come into play. Water is transferred from land into the ocean, and the solid Earth relaxes back to the original equilibrium, leading now to a sea level rise, both because water is entering the ocean from land, and also because the coastal elevation is decreasing relative to that of the surrounding water. The response of the solid Earth to changing loads caused by the growth and decline of ice sheets is very slow. And so at present, the Earth's crust and mantle are still experiencing changes in elevation resulting from deglaciation. This process is called glacial isostatic adjustment. This map shows how the Earth's crust is still deforming today in response to the last deglaciation. In regions that were covered by large ice sheets that have now disappeared, namely North America and Eurasia, or in areas where the volume of ice was larger than at present, notably in Antarctica, the crust is moving upwards at rates of up to a few millimeters per year. Surrounding these areas of uplift, there are regions where the peripheral bulges are subsiding, and so the crust is sinking rather than rising there. Interestingly, note that this is happening in the southern North Sea and in southern Great Britain. The seafloor of the central North Sea is subsiding at a rate of about 1 millimeter per year, while southern Great Britain is sinking at a small fraction of a millimeter per year. Meanwhile, the highlands are being uplifted by almost 1 millimeter per year. So, in certain areas of the world, including the North Sea, which has been the focus of our attention, the effects of glacial isostatic rebound will locally counter in a very small part the effects of sea level rise caused by global warming. We come back almost full circle to the early parts of this talk when we discussed global warming and global sea level rise. Modern sea level rise will continue apace for many decades, if not hundreds of years, even if mankind is successful in reaching net zero emissions in time to avert global temperatures rising above the golden 1.5 degrees target. This is simply because the timescales at which the ocean and the climate operates differ considerably from human and especially political timescales. The UK Met Office have calculated projections of sea level rise around the UK following various possible scenarios of climatic change. Projections are shown on this slide for the North Sea ports of Edinburgh and London. We do not need to enter into the finer details of these curves. RCP 2.5, 6, 4.5 and 8.5 represents different carbon emission and policy scenarios. The solid curves indicate the projected sea level trajectories over the next 300 years for each scenario. We can see that sea levels will continue rising in the North Sea, perhaps by as much as 1 meter in the next 100 years or so. And these changes in sea level will no doubt shape the future of the North Sea in the same way as past sea level changes have shaped its history. If an unknown civilization had built a statue of liberty in some ice-free port along the southeastern coast of North America at the time of the last glacial maximum, certainly not at New York, as New York was covered by ice at the time. That statue could today look something like this. Sea level rise in the next few hundred years is unlikely to be anywhere near as dramatic as it was during the early Holocene. Nevertheless, sea level changes caused by global warming could lead to a Liberty Island ending up underwater, like so. And this is perhaps a sobering enough image to conclude this talk. Many thanks for your time.